there's actually a different way of solving a derivative function, one way that we have not yet covered, which is called differentiating implicitly. And let's go ahead and look into that. But essentially, it's a helpful method of solving a derivative when either our equation is too complicated or we don't necessarily want to solve it as a function. And so, like, in general, in calculus, we study functions, like, and remember, definition of function is y is equal to f of x. Like, we have an equation solved for y, like, for example, x squared plus 7. And then, we have a specific notation, which we're dealing with things specifically set for f of x. But as we know in math, it's not always solved for y. Like, sometimes we have an equation of a circle, for instance, x squared plus y squared is equal to 1. And let's say we want to know what's the derivative of that when something is not a function. Implicit differentiation can be used sometimes in order to determine the slope of a tangent line for, say, a circle or something which is not a mathematical function. And the simple idea is basically taking the derivative of both sides. So sort of like in an equation, I could subtract y squared from both sides, or I could add 3 to both sides, or divide both sides by 2, right? I can work with both sides of this equation. The key logic is that since this is assumed to equal to this, as long as I do the same thing to both sides, I should be fine. And now there are some restrictions in math when that logic falls apart. For example, squaring both sides. Like, say I had -1 is equal to 1. That equation, you can definitely believe that that is not a true equation. But let's say I were to square both sides of this equation. Square this. 1 is equal to 1. Now it appears to be a true statement. And so something a little bit strange happens where if you do the same thing to both sides, it doesn't always mean it works or is true. And really, you're only allowed to do this in certain cases. When you're dealing with one-to-one functions is typically the rule. But like with differentiation, assuming that your functions are differentiable, there are some technicalities here, but at the end of the day, that's kind of the idea. If you differentiate both sides, you can find the derivative that way. So let's consider an example. Let's consider the equation y cubed is equal to 2x. So again, this is not in function form because it's not y by itself, but we could take the cube root of both sides since the cube root is a one-to-one function. Now again, with square roots, there's certain things that make it so that you can't do this. But if I was to take the cube root here, which is totally fine, I would have the cube root of y cubed is equal to the cube root of 2x. So again, it's kind of like I'm doing the same thing to both sides, and this is allowed. And if you remember from algebra, cube rooting a cube will cancel it. That's the whole point. That's the reason it exists. And this would give me y is equal to the cube root of 2x. And so now I have it solved for a function. And if I want to know, well, what's the derivative, dy dx, I can now just apply my normal derivative rules because it's, I could also write this as f of x. And if I want to find f prime, well, I just need to know the derivative of this now. So, in this case, I could do that by, I could rewrite this as 2x quantity to the 1/3. Since it is, as we know, nth roots correspond to fractional exponents. And then finding dy dx is just a matter of applying the power rule. So, I have 2x to the 1/3 power. I could drop the power. This would give me 1/3 times 2x and subtract 1. 1/3 minus 1 would be -2/3. And don't forget, very easy to forget here, is I also need to use a chain rule because anytime there's anything more than just x on the inside, I need to multiply by the derivative of the inside. And since the inside was just 2x, derivative of 2x is 2, and that will pop out, as I like to say, as a multiplier by the chain rule. And so this would give me my derivative. And we could clean this up. This would be 2/3 divided by 2x to the 2/3, which would be the cube root of 2x squared. 2x squared would be 4x squared because we need to square that. And again, don't necessarily need to change how we write it, but that would be about the neatest, most common way of writing that answer. Anyways, so the whole point of that is not to look at derivatives once again, because we've taken lots and lots of derivatives at this point in our class. But I wanted to look at how do you do it differently? How do you differentiate this equation implicitly? And essentially, it's like the differential operator ddx can be applied to both sides of the equation, again, in certain circumstances. So if I was to take ddx of the left-hand side and ddx of the right-hand side, how would that work? And how would I do that is the question. So, well, the right hand side of this equation is very simple. We know the derivative of 2x is just equal to 2. That's easy. But the question is, well, what's d dx of y cubed? And one thing you might think is, well, Professor Havens, you told me earlier that if they don't match up, this is treated as a constant and the derivative of a constant is a 0. And that's not, well, that is wrong, but that is a true idea in some cases. But the thing about this is y, as it's stated here, is not a constant. It does vary with respect to x. So the issue here is this is not constant with respect to x, because right here it says it's based on x. I just don't know exactly what it is. So the thing you might be wondering is, well, how do we do this? But there's a very simple rule. Basically, if you want to take the derivative of a different variable when it is a function, like here, y varies with x, it is not a constant. But I can still take the derivative of it. Basically, I just take the derivative normally, 3y squared. The issue is, in here, I'm imagining this is not just y. This is dependent on x in some way. So what needs to be done here is I need to use the chain rule. And that's the key thing that you need to remember if you're going to differentiate implicitly. Anytime we're doing implicit differentiation, you can differentiate the y, but you need to use the chain rule. And what all that means is, well, I need to also multiply this by the derivative of the inside. And again, I don't know what that is, but that is dy dx. And this is what allows me to solve a derivative in this way, is that the derivative of the interior pops out dy dx. That's what I'm looking to figure out. What's the ratio of dy dx in this particular case? And notice actually from here, I can directly solve this simply by dividing by 3y squared, because basically now that I have a dy dx in my equation, that would leave me with 2 over 3 times y squared. And notice that since we found y up here, y is equal to the cube root of 2x. Notice that I could substitute y. Technically, we could leave the derivative in this form. It looks a little weird leaving y in my equation when it was originally dependent on x, but that's totally fine in certain circumstances. But usually, since this is a derivative function with respect to x, usually I want my answer in terms of x, like up here. And basically, well, y is the cube root of 2x. So this would be 2 divided by 3 times the cube root of 2x squared. And of course, again, like up here, there's a rule for roots where if you're squaring an entire thing, you can just square the interior and that is equivalent. So some more intermediate algebra review, but this would leave us with 4x squared. Because again, 2x squared is 4x squared. And what I get is exactly the same thing. So that's kind of my initial point here, is the derivative done implicitly should be the same as the derivative if done normally or just by using functional rules that we're dealing with. The process is just a little bit different. And the thing to remember here is, and like with the case of the power rule, notice like if I take the derivative of y, k, assuming x is a function k, notice what it says is, well, I'm going to use the power rule, drop k, subtract 1 from the exponent, but also multiply by dy dx. Essentially, if you're ever differentiating anything with regards to y, you need to multiply by dy dx afterwards. Otherwise, you're just using normal differentiation rules. But, when I'm differentiating over here, I don't need to do that. So let's do one more example. It says for this equation, which is a lot crazier, it says find dy dx using implicit differentiation. So, again, at the end of the day, the first step is the same thing. I'm going to take the derivative of both sides with respect to x, which is what we mean when we write d dx. And then from here, I just need to solve write equals there. We just need to solve each derivative portion. And so on the left-hand side, well, the derivative of y cubed, again, here I need to remember, okay, this is not just 3y squared. It's going to be 3y squared dy dx. And how a lot of people write it is using y prime. Another notation for derivatives, which I think I mentioned before, but I don't really use it. It's very common in physics to write derivatives this way, but essentially it's just another shorthand for dy dx. Just like we write f prime, right? F prime of x, it's just a shorthand for derivative. Y prime also means that. So this is how a lot of people write it, but I'm going to use the notation. I'm going to try to be consistent with our book and using Leibniz notation instead. But anyways, yeah. So again, derivative of anything with y, you need to pop out a dy dx. Now looking at the next term here, another thing that would be easy to miss is now that I have something times something, this I actually need to use the product rule here because it's not, I can't just take the power rule because it's two things multiplied. So applying first d second plus second d first. Well, first d second. Well, again, now notice how I'm taking the derivative of y to the fifth. So that'd be 5y to the fourth. And since it was a derivative involving y, I need to also multiply by dy dx. So I have first d second plus second d first. So again, second d first would be y to the fifth times 2x. Here I don't need dy dx because I was differentiating with I was doing d dx of x squared, which is just 2x. So another way you could remember it is if you're doing d dx of x, it's just normal. But if you're doing d dx of anything involving y, you need to multiply by dy dx whenever taking that derivative. And then the last one on the left-hand side, d dx of x to the fourth is just going to be negative 4x cubed. And again, don't need dy dx there. Now on the right-hand side, we just have d dx of 27. And remember, derivative of any constant is always 0. And so now the question is, well, where do I go from here? I finished differentiating my equation. Now what? Well, again, the goal is to solve for dy dx to get it by itself, like I did here. So basically, we're going to need to do some algebra. And the goal is to put all terms involving d dx on one side, and then factor out everything else. Factor out the dy dx. And then I could put everything that does not involve dy dx on the other side. So essentially, I want to put those two things on the right-hand side of the equation by adding or subtracting from both sides. So I'm going to leave the first two terms on the left-hand side, and I'll go ahead and rewrite them in a more sensible order. And then I want to subtract this guy over there. So that would be minus 2xy to the fifth. And I want to add that guy over there. So that would be plus 4x cubed. And now I've put basically put all my dy dx terms on one side, put all the other terms on the other side. And now on the left-hand side, I could factor out dy dx because it is a common factor. Again, I can treat it just like a variable, like an algebraic entity. So I would have dy dx multiplied by, let me make this a little less ugly. Dy dx, man, just the y is not coming out. Dy dx multiplied by, so if I factor out dy dx, that would leave me with 3y squared plus 5x squared y to the fourth. And then on the right-hand side, I have negative 2xy to the fifth plus 4x cubed. And it's also worth mentioning here that, remember, d dx means take a derivative. Dy dx is the derivative by itself. So this does not mean take the derivative of this. This means that I have a derivative and it's multiplied by this. So a subtle difference here. And if I want to solve the derivative for this equation implicitly, now I have dy dx. Now I just want to divide all this away because this is just this times this. I could divide both sides by 3y squared plus 5x squared. So that would be, well, I have my right-hand side of my equation, and I want to divide it by all that other stuff that was left. 3y squared plus 5x squared y to the fourth. And this would give me my derivative done implicitly. And again, it's like I said before, it's often okay just to leave it involving y, because trying to figure out, well, what is y? How do I even solve this equation for y? It might not even be possible because it's not even a function to begin with. So whether it is or isn't, doesn't matter. Leaving a derivative is totally fine like this. Because let's look at an example. Like in this case, let's say if you're wondering what the heck does this sort of equation look like, it looks like a little bit of a nub, but this is an implicit plot of this equation. Again, we would sometimes say the equation is an implicit equation, and that term often comes from an equation which is not a function, not solved for y, and typically indicates the equation is more complicated. But here's our graph. And let's say we wanted to know where is the maximum point, we wanted to do calculus stuff to solve things about this curve. Well, we could differentiate it implicitly, solve dy dx, again, involving both x and y. But then if we want to, figure out where that point is, or, as the example says, find the slope of the tangent line at the point 0, 3. Well, looking at this, it appears to be a maximum, so it's probably going to be 0. But let's just plug it in and see what happens into our derivative. And, if we wanted to find the slope anywhere, we could do so just by plugging it in. But if we plug in, another way that this is often written is if we wanted to evaluate a derivative at a particular point in time, we kind of write it using this line, which is kind of an unusual notation, but sometimes still used in certain calculus texts. And you might see it here and there. But all that kind of means is it's just like f prime of x. So this is a derivative I'm evaluating at this point. And however, this would not be f prime of x. It would be called a multivariate function because it would involve both x and y. But anyways, we'll plug in 0. And if I plug in 0 and 3, well, this would all go to 0. I'd have 0 plus, 4 times 0 divided by 3y squared would be 3 times 3 times 3 is 27. And then 5 times 0 is going to be 0. So I would end up getting 0 over 27, and I do end up getting 0. So again, what I could determine from that is that's a critical value that should correspond to a local minimum or a local min or max, and blah, 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 other calculus stuff. But at the end of the day, we can see that this derivative does make sense for its implicit plot, and we could find other things like, well, notice there's actually another local min here and here. We could solve those, et cetera, et cetera. Anyways, that will wrap up this video on implicit differentiation.